Okay. Good morning, everybody. I hope everyone's having a wonderful day. So today I'm going to be talking about more with heaps and priority queues today. So the first thing I'm going to do with you today is I want to talk about how I can take an arbitrary array of length n and convert it into a minimum heap. So that's going to be the first thing we're going to address. And then what we're going to do is we're going to transition over to talking about a couple of applications we can do with heaps. So hope you had a good weekend. But first, I want to really kind of touch upon something involving heaps. Now, one natural question that might pop up, if you think about it, is I showed you an array-based implementation of a binary heap. It was very simple to interpret. You can imagine the tree structure, and you have a very easy way of computing where certain elements will be in that tree using the array representation. And now a great question would be, okay, how can we make a heap? So imagine if I gave you an array of length n, so it has n elements in it, and I would like to be able to take that array and create a heap out of that array. So whether it be in the array itself or build another heap out of all those elements. So a naive approach would just simply be taking each one of these elements in this array and you insert it into a heap. So of course this would be a way you can build a heap, and this will take big theta and log n time, right? Because each one of those operations for the insert operation takes big theta log n. And if I do n of them, then it's n log n, right? But imagine, the real question is, can I do better than this? And now the neat thing about this I'm going to show you is that the answer is yes, you can do better. So often this kind of view of things makes a lot of sense when you think about having all the elements, say n of them, well in advance. And I want to build bottom up a heap. Now, I'll tell more about what I mean by bottom up in one moment, but I'm going to show you how you could do this in linear time. So imagine I give you an array like this. I would want to be able to turn this into a heap. So I want to take this and make this into a min heap. So that's the goal. So right now it's presently not a heap. So I would need to do something to this. And now there is a way I can do this. So here's an algorithm, and I'm going to call it heapify. And it's actually surprisingly simple in the way it appears. But the analysis is quite tricky with the actual analysis that we're going to do right here. So first, I'm just going to assume this array, and I'm going to call it L, exists. And it has n elements in it. And what I would like to do is I would like to result in getting A to B. Actually, sorry, let's call this A. For some reason I called it L there. Let's call it A. Getting a little excited here. And what I would like to do is I would like to turn this into a heap. So I'm just going to assume this array A already exists. And so in terms of an implementation, you can imagine this array is actually built inside of a class. And all I'm doing is running this on it. So this would be a method inside of my class. So what am I going to do is I'm going to start right around the middle of the array. So technically this is going to be the position of the last element. Now recall that if ever I want to compute the parent of a node in the heap, or an element, or say if you think about it as a position, remember if I give you some position I, if ever I want to know the parent, it's I minus 1 over 2. Well, recall that if I'm at the end of that array, that position is n minus 1, right? So instead of it being I, it's n minus 1 all over 2. And this simplifies to n minus 2 over 2 rounded down. So this is actually the position of the parent of the last element. So this will be where it's going to be located. That's where we're going to start this so-called heapify process. Now, you might ask, Dan, what are you going to do? So first, I want to kind of just draw you a quick little doodle here. A doodle here. And I want you to imagine you have a heap. And I'm going to fill this in as we do our example in a moment. But the thing I want you to observe what I would like you to observe is by selecting the parent of the last element, that gets you up here. That gets you one level above. Oh, I lost my turtle. Oh, I'll save him later. So notice that by doing this, all of these nodes in my heap, all of them are indeed at the bottom. And what I would like to do is I'm going to bottom up build the heap. And by bottom up, what I'm going to do is I'm going to imagine like I look at each one of the positions from, say, in this case, so say I look at everything to the left of where I just drew this big line, everything over here, I'm going to imagine like I'm almost inserting each one of these. Actually, well, technically it's more like the process when we do the removal, but the point is I want to imagine like this just came poofed into existence in the heap, and I would like to put it into the spot where it belongs in the min heap. So for example, when I look at position 2, this would be where the 7 would be located, right? So 7 would be right here. So you'd naturally look at this and say, hey, look, Dan, that 7 is clearly much bigger than the 1, and I want to maintain a min heap. So what's the first thing you might think of doing when you want to fix this? You'd want to try swapping the 7 with the 1, so that the 7's down here, and the 1's up here. So I'm going to consider more and more of the elements as I scan to the left in this array, and I'm going to perform, and the process I could do this with is bubble down. Yeah, I swap 1 and 7, perfect. So that would be exactly what I would do. And now notice, hey, look, this is like if I now have the heap looking like this so far. So I'm going to be building it up bottom up by considering more elements and introducing them into the heap from the right here all the way to the left, because this is like me going level by level, but bottom up. That's what I mean by bottom up. And when I do this, I'm going to use bubble down, starting at that position, and I'm just going to simply apply it like we did last time. So where I'm going to perform those swaps, and I'm going to try dragging those more heavier elements to the bottom of the heap. So I just use bubble down, and then I decrement the start index, the one I said it was at the parent of the last element. I'm going to decrement it by 1 each time until I get all the way furthest to the left. And once that is exceeded, as in like now start index becomes negative, then I know I'm done. So I don't have to do this anymore. So I'm just going to consider each one of these elements. I'm going to introduce it into the heap, and then I'm going to perform bubble down for each one of them. So let me continue this first. Are we okay with this so far? So far what I've done is I've actually done the very first iteration of this process. So I did the bubble down where I swapped 1 and 7 as somebody had suggested I do. And then now I'm going to decrement the start index by 1. So now I'm going to consider everything now to the right of this, and I'm going to introduce 2 into here. So if I put 2 in, so imagine it's going to go right here. Is 2 okay here in our min heap? Is it okay right there? So imagine this as a smaller heap, just like I did over here. I'm going to consider this a little heap. Like look, it's like a little cute rinky-dink version of the overall heap, right? So I'm building smaller heaps to build the larger one, bottom up. So is this technically right here a min heap? This right here. Yeah, yes, it is. It is. So what I'm going to do is this is what I mean by bottom up. I'm going to build successively larger heaps so that when I'm done, I have the heap for all the elements. That's where the idea comes from. So now now I've done this iteration. So notice I didn't have to bubble down there anymore because it's in the correct spot. Then I decrement start index by 1. And now I'm going to introduce 8 into this. So I'm going to introduce 8. Now notice I've incorporated all the elements, but there's a problem here. This is not the minimum element of all these guys here, right? Does anybody have any suggestion of what I should be doing with this bubble down process? Now just remember, last day we established that when I'm doing bubble down, I always select, if I have two children, I always select the one with the lesser key value. So you know that there's going to be a swap that happens. What am I going to have to swap? And there may be more than once this is going to happen. Can somebody tell me? I'll start going this way. Yep. So we got 1 and 8. Perfect. Pointed out in the chat. Awesome. So I'm going to swap 1 and 8. So I swap these two. So I swap them. Am I done yet? Am I done yet? Yes or no? Am I done yet? No. Perfect. Perfect. Good, 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 good. So I'm going to perform another swap, right? I'm going to have to swap 7 and 8. So I'm going to swap these two. And since I only have one child, I automatically just select the one that's the left one. There never will be one on the right if there's only one child. That's because of the heap property and the fact that, actually, well, technically it's the complete binary tree property, but both of them together guarantee that fact. So now do I have a minimum heap? Are we all good now? I think we're all good now, aren't we? Yeah, we got it. So now, does everybody see what I just did? So notice that so what I've done is I've started off with these very small min heaps at the bottom, on the bottom level. And as I scan from left to right from roughly about the middle, notice that every time I incorporate another element, that will be on the level just above it. And that will cause me to create larger and larger heaps. And when I'm done this process, I end up with the overall min heap. So just because I noticed that I wasn't doing any of the updates here, let me just fix this up. So let's just write this out. So remember, an easy way you can read off the min heap would be, in fact, just to read it from level by level, left to right. So what you'd end up with is 1, 2, 7, 3, 4, 8. And that's basically heapify. So it's surprisingly simple. And the question is, how do you know it runs in linear time? That's the real question that we're going to have to quickly address, because the analysis is a little technical. So the first thing you might say, Dan, when I analyze this, so notice I do this assignment here, and then I do this loop. Notice that start index starts roughly around the middle there. And I do this process, say, order n times. So you can think of it as, because I start around the middle, right? And the length of the array is n. And this bubble down process I know takes big theta of log n. And I decrement this, right? So this is going to happen roughly linear time, but each time I do the logarithmic operation. So a very crude analysis. So if I wanted to do a crude analysis, so a crude analysis of this would just simply be that I claim that it's like big O of n log n. So I just say it's big O of n log n, or big theta n log n. That's my very crude analysis. However, that isn't quite, actually, I'll just leave it as big O. This is a crude way of analyzing this. Why? Because of a very interesting property that I was trying to allude to as I was doing this bottom-up process. So whenever I incorporate another element into this, so when I'm building up my min heaps, notice that when I get here, do I consider the entire heap when I did that bubble down process right here? Do I look at the entire heap when I do this? Well, I look at it only from the context of the smaller heap. I only look at like what's right here. That's it. Right? Likewise over here. When I incorporated the two, I started right there. Notice I'm not looking at the entire heap, so it actually isn't really that the paths that these swaps can take to go down, all the way down to the leaves, isn't actually going to be that big, at least for most of the operations. It's only once you incorporate the entire heap will you start getting those types of path lengths. That's why, because I'm building these successively larger binary heaps. So the analysis goes like this, and I want to just point out two facts, and then I'll kind of quickly whip through it because I'll have more details in the notes because I want to talk about more stuff with you today. But I want to just give you the general idea of how the analysis goes. So there's kind of two properties you need to be aware of about heapify. So I alluded to both of them. One that we're dealing with, that every time I do one of these bubble down processes, it isn't actually going to be dependent on n all the time. It's actually dependent on how long this path can be. And as I'm making larger and larger heaps, it's going to not actually be the full length of that's maximally possible. It's actually going to end up being a lot of time much smaller. So I'm going to have kind of two facts I want to throw at you that I'm going to use for my analysis. I have a much more carefully written way of talking about this in the notes, but I want to give you kind of two facts about this. The first one is much harder to see. The second one's much easier. It's actually directly what I just said a moment ago. So the first one is the maximum number of elements in a heap of size n is equal to 2 to the power of h plus 1 minus 1. Now, if you're curious how I got that, I just summed it level by level. And I imagine that this has it where every single node on the final level is filled. So you add those up, you end up getting a geometric series that you can easily sum up, or you can use another closed form. There's other ones. Like you might use the binomial theorem. There's a lot of ways you can derive this. Those are the couple I could think off the top of my head. So the question I have for you, now this is where, like I said, this is not going to look very easy at first, but I'm going to kind of point it out to you. So how many nodes are there in a heap of size n whose height, now when I say that, I mean if rooting, so imagine like in my process where I drew this picture and I told you that once I incorporated 7 into this, I treated that as its own heap, right? So that's what I'm referring to as the height. I'm rooting it at that node when I'm talking about it in this context. If rooting its subtree. So if rooting its subtree, so I'm imagining this as the subtree rooted at 2, for example. So it says if rooting its subtree. If rooting its subtree, whose height is I. So imagine I tell you that the height of this subtree is in fact I. So just to use this picture to help me illustrate this idea. So if I look at all of the nodes on right here, this one, and this one, all of these have height 0 with respect to those nodes, because notice it has no children. So if I look at this one and I just isolate that one has height 0. All the ones right here, these all have height 1. And the one at the top, that one has height 2. So remember, I'm just looking at the node itself, and I'm imagining its subtree. In this case, I'm considering the entire tree. But notice that maximally, the number of elements that could exist, there could be another node sitting right here. So what I want to do is I want to make this as big as possible. So if I tell you that the overall number is going to be this n here, I want you to think about this. On level 2, so if I consider the nodes at height 0, and I want to know how many of them there are in this heap with n elements. So imagine there is a node just sitting right here as well, because that's the one with the maximum number of elements for this given heap structure. So notice that this starts at 4, then it goes to 2 as I increment I, and then I can go down to 1, right? So notice that this has an interesting pattern to it. Notice that if I had another level down here and all of them were filled, how many would there be? Can somebody tell me how many would there be? So if the first one up here only has 1, then there's 2, then there's 4, then what's going to go right here? 8. Yes, exactly. People are catching on to the pattern here. So you might ask, okay, well, how do I capture this? Well, here's one way, is I can, the answer to this, I'll let you think about how I got it. It's n over 2 to the power of I plus 1. So I encourage you to take out this and just see what it looks like when I plug in for I into that formula and see if it checks out with each one of these as a bound on the number of nodes at that given height. So that's the first piece I need, is that. And the second one, this is the one I already said. The second one I had said, the bubble down. So remember, bubble down depends on how many swaps you perform, right? And when I'm say right here, it isn't that really that I'm considering the whole height of this heap, right? I only have consider, since it has height 1 at this stage, notice that if I is the height of that subtree, then how long does bubble down take with respect to I? Well, it takes big O of I time, where I is the height of the heap. So that's where I comes from. It's that, notice that I don't actually have to start at n. So sorry, remember, it's not log n. That's the height of the overall heap. I'm just talking about the parts that I'm building up from bottom up. Why? Because remember, this is actually just the number of swaps that happen. So what I'm going to do, now this is the trick, is that I'm going to sum over all the levels of my tree. So I'm going to count up all the work that's going to happen across all the levels that I do all of this stuff on. So I'm going to say, so by summing over all levels of the tree, heapify takes when the tree has height h, so imagine its height is h, is the following. Now this is where, sorry, I get a little excited about this. I'm just going to erase this part here on the heapify pseudocode. This is where, you know how I talked about big O notation and whatnot, and I said, oh, there's a couple of useful ways to use it. I'm going to use that second approach here, and you're going to see how handy this can be when I'm writing out things that are a little bit more complicated. So I'm hoping I can give you some appreciation for it. So when I take the sum over for a given h for the height, this is what I'm going to get. Now, don't be spooked by this. Just watch carefully. So I'm just starting back from up here. So I'm going to have, I start at 0 all the way up to h. So I'm just trying to represent all levels of the tree. I'm just being very charitable with myself. So I know that each time I'm going to do a bubble down, right? So I'm going to do bubble down. And I'm going to do it how many times? it depends on fact 1, right? This is how many nodes there are at a given height, right? So I'm just going to plug that in. So each one I'm going to do bubble down at for a given I. So I have n over 2 to the power of I plus 1. That looks rather complicated, doesn't it? We haven't done anything where there's a big O hiding in there. Now watch this. This is the slick part about using this type of usage. Is that because I said, okay, it's just some constant times I, right? That's with some n0 that's kicking around. Well, I can capture all of this by just taking big O of everything. So I'm going to take n times. So I'm just going to pull this n out because when the ceiling is there, it doesn't really add anything with respect to big O. So I'm just going to pull that n out, 0 to h, and I'm going to have I over 2 to the power of I. You might ask where the plus 1 went. Remember, I could factor out that extra 2 in the denominator as another constant factor. That's where it's gone. It's gone. It's gone. It's gone. It's been absorbed by the big O notation. That's where it's gone. So now, you might ask, okay, well, what do you do with this? Well, I'm going to do something that you would first not really think of trying to do, unless you really know things about infinite series. Watch this. So I'm going to say this is big O of the same thing, and I'm going to sum from I is equal to 0 to infinity of I over 2 to the power of I. Like I said, this is not an easy analysis. I must stress that. But if you're following me, you're doing pretty good. So now you might ask, Dan, how do you evaluate this? And the fortunate thing that we do know is that this sum converges. So it means it's going to have a value. And it looks like something that's we haven't seen actually a closed form expression for even a finite version of this, but I'm going to give you it. So this is going to end up being n times 1/2 over 1 minus 1/2 squared. And you might ask where this comes from. Well, this is actually from another closed, it's actually a nice sum when you have a multiplicative I kicking around. And then you also have something that looks like a geometric series kicking around. So if you're wondering where that comes from, it's from the following. It's as the sum from I is equal to 0 to infinity of I times x to the power of I. And this is actually equal to x over 1 minus x squared. This is if the absolute value of x is less than 1. I would never ask you to recite this at all for me. I just want to point out that fact for you. It's interesting. It's always handy to know series analysis like this because it sometimes creeps into these things. But now you might ask, okay, well, what do you do with this? Well, that's all constant, right? And we're good. Boom. There's the big O of n. Didn't we do a lot of work to get the big O of n? But it's by no means simple, right? It took a little bit of careful thinking about how the algorithm actually operates as opposed to just blindly applying the overall operation, right? So sometimes in data structures, when people study these things, they often have to look very carefully at properties that the algorithm actually has. And you end up actually getting tighter results as a result of that. So are there any questions about that? So heapify you could do in linear time. So if I give you an array, you can turn it into a min heap in linear time. I must stress that, as I'm going to mention in a moment, this is also true for a max heap. So are we all okay with this? So if I lost you somewhere in here, don't worry. Just think about it a little bit more. Remember, I'm trying to suppress the constant terms or constant factors that pop up in this thing. That's what all I'm doing. I'm being sloppy. But I wanted to show you an example of using it in this way, where I'm using the big O notation, but notice I'm using remember, that's not an equal sign. It's just, I'm saying that is this, and then I keep repeatedly doing this. So isn't that neat? So now you know a way that you can take an array-based implementation of a heap, and you can convert it from just any old array in linear time. It's pretty slick. Okay, so now we're going to be moving on to our first application for the day. You're going to find I'm going to kind of go through these a little swiftly because I have more details in the notes if you want to really just dive into this a little bit more. So the first application I'm going to talk about is sorting. And it uses the thing that we just talked about. It uses heapify. So let's talk about sorting. So I want to first present you a scenario. And I'm going to explain the trade-offs between different various data structures for priority queues and show you that there's actually a direct connection between sorting and priority queues. Mind-blowing. Mind-blowing, but we're going to see this. So imagine I'm given an array A of n objects. Imagine you can create a priority queue. So imagine you create a priority queue. From this point forward, I'm just going to abbreviate this as a PQ. I think I've done this already last day as well. So I want you to imagine you can do the following. So I'm going to perform an insert on each object in A. Perform an insert operation on each object in A. And I'm just going to assume, of course, that when you do these comparisons, they all take constant time. So imagine you do all these insertions. Then copy back into A from left to right. From left to right. Each object received on a remove min call. So just imagine the following scenario. So imagine I give you an array A with n objects. I'm going to make an empty priority queue, and then I'm going to perform n insertions. So I'm going to insert each one of the objects of A into my priority queue, and then I'm going to copy back the results from left to right on each one of my remove min calls. So remember, when I use remove min, I end up getting the minimum valued key, right? So if it makes it easier to imagine this, just imagine I have an array of numbers, and I dump them all into my priority queue, and each time I get the next smallest element, right? I do that each time. And I copy it back in. What do I end up getting? I end up getting a sorted array. The result is A is sorted. So that's not even the interesting thing I really want to talk about, but the fact that you could do this is nice. But so the big thing I want to point out is how you implement the priority queue. How you implement the priority queue determines its efficiency. That's the first kind of obvious thing. Determines its efficiency. And its relationship with sorting. So I'm going to consider 3 different ways I can implement a priority queue. We talked about 3 different ways, right? We talked about having a sorted and unsorted doubly linked list, which I can easily contract to being a sorted or unsorted array or list. So I can take an unsorted array or list. And you may recall that, okay, based on what we described a little while back, that I could do what I just described here. I do n inserts, then I do n remove mins, right? So each one of those will take me take me with respect to an unsorted array. So remember, the first bunch where I just dump them in, so I do insertions on an unsorted array, those all take constant time, right? So I end up with n constant time operations. The second part is the nasty part, where each one of these remove min calls takes linear time, and I do n of them. That means that the running time of this will be quadratic with respect to the length of the array. Now, the neat thing I want to point out is that this is actually going to correspond to selection sort. So this actually corresponds to selection sort. You might ask, Dan, where the heck did that come in here? I don't remember talking about priority queues when I was talking about selection sort or some other sorting algorithms. Here's what I want. I'm going to do one of these two with you just to give you the idea of where this is coming from. So I want you to strip away the abstraction of having insert and remove min calls and just look at what happens to the array. So I'm going to draw a little table here. So I'm going to imagine I give you an input sequence that is 4, 3, 1, 2. So you can imagine this as your unsorted array. Sorry, the array A. So imagine this is A. So imagine this is A. And then imagine I have my priority queue. There's two phases to the process I described above. The insert phase and then the remove min phase. So I have this insert phase that happens first. So I first perform those n insertions into the priority queue. And then I do the remove mins. So if it's unsorted, and this is the thing I want you to pay attention to, there's really going to be two parts in selection sort. I want to just remind you, in selection sort, as you perform the sorting, there's going to be a partial part of the array that's going to end up being partly sorted. So meaning that it's going to be sorted up to that point, and then everything else might be unsorted. So what I want to show you is how that pops up in this. So imagine I do a whole bunch of insertions. So first, my priority queue starts off as empty. Imagine I have an empty priority queue. And actually, let me put it up here. Makes a little bit more sense that the priority queue is currently empty. So the priority queue is currently empty. And what I'm going to do is I'm going to insert them as I would as I described here. So I'm just going to insert 4. So that means that my sequence, so this is the part, like this is technically the part that I really want you to pay attention to, is watch, when I insert 4 in, it goes into the priority queue. And then when I insert 3, so I'm going to scan from left to right, I'm going to insert 3. 1, 2. Remember, it's an unsorted list or array. So it's going to be 4, then 3. Remember, this is what I did with my doubly linked list, right? I just dumped it in there. Whether it be on the front or the back, it didn't matter. And then I put in the 1. Sorry, the 2. Yeah, let's put the 1 in. Let's put the 1 in. Now let's see. 4. Yeah, let's put in the 1, yes. Getting a little ahead of myself. We're putting the 1 in, so 2 is going to be left on that side. Then I end up with 4, 3, 1. And then, when I insert the 1, this part here becomes empty. So I have 4, 3, 3, 1, 2. So notice that the priority queue just doesn't keep track of the ordering at all. So what happens? Well, now we have this remove min phase. So we have the remove min phase. And what's going to happen is I'm going to go through each one of the elements on the priority queue, and I'm going to go remove min on it, right? So I start off with this being all of these elements, 4, 3, 1, 2, and my sequence is going to be empty. I do remove min, I remove the 1, right? 4, 3, 2, and 1 will be right here. I do another remove min call, and then I get the 2 out of there. And I'm copying them from left to right. So notice that as I'm doing the remove min calls, everything on this side is going to be sorted. Everything on that side may not necessarily be sorted. And now I remove min, which will be 3. So I end up with 1, 2, 3. And then, of course, I do remove min again. The priority queue becomes empty, and I end up with a sorted sequence of elements. So notice that in this process, that this, if you look, I want you to think about this because I just really want you to think about it a little bit. This is kind of like selection sort. Just if you remove the parts that I do these insert operations, you think about me manipulating the array directly. And take out all of that fancy-pantsy stuff with the ADT. You'll notice that this actually does very much the same execution call as selection sort would. So that's one correspondence. And now you might ask, and actually I have a question for you based on this idea. So you can think of this as like my partitioning of the array into the sorting part and the unsorted part. In selection sort, the sorted part ends up coming out in the remove min phase. So my question is, what happens when I give you a sorted array or list? So what sorting algorithm do you think that's going to look like? I'll tell you that this is going to take it's going to take big theta n squared to run. But think about it. Can you think of a sorting algorithm where as soon as you dump them in, remember this is a sorted list, so whenever I put one in, it's going to remain in the sorted spot, and anything else is going to get shuffled that way, to its right. There's a sorting algorithm that does something like this. It's insertion sort, perfect. This corresponds to insertion sort. So if you're not convinced by this, I have an example quite like this in the notes. But yeah, so I want to point out that priority queue is actually closely related to sorting. So this little scenario I just gave you is another way you could think about how you can sort an array. And it's just using priority queues. Is that kind of neat? So now the question is, what happens when I give you a heap? That is the real question. So now, let's think about this when I give you a heap. Okay, now imagine I take the priority queue and I implement it as a heap. So imagine I use a binary heap to do this. So imagine I have a heap. Now, each one of my insertions, so each insert operation takes big theta log n, right? So it means it's going to take n log n to do all the insertions. And each remove min takes, remember we established that I end up with this log n for the remove min. And remember, I just showed you how I can take an array and I could build it into a heap so I could set it up for this. But I'm not going to worry so much about that right now. I'll get to that in a moment. So just assuming the scenario I had before, I just dump them all into a heap and I do the remove min calls. So overall, this takes, okay, well, this is n log n to do all the insertions and n log n for the removals. This takes big theta n log n time, and that matches our lower bound on comparison-based sorting, right? We said that earlier in this class. So that in itself isn't the part I really want to focus on. Notice in my scenario, I build a new structure to contain all the elements. I want to focus on the space that's get used. So I say we, however, use big O of n additional space. Additional space. Why? Because remember, I build the binary heap. I would like to have it where I could get rid of that additional space, so I use a constant amount of space. So I give you my array, and I want to use no more than a constant amount of extra space. So I just basically want to have a bunch of variables kicking around and just the input array. That's what I want to do, is I want to eliminate that space. So I've shown you how you can easily do this sorting process using a binary heap. That brings me to talking about an interesting question I have, is how we eliminate the linear extra space. So how do we remove this space? So what the first thing you might point out and say, Dan, well, we never talked about max heaps up to this point, so why do you want to talk about a max heap? So first, I'm going to suggest we use a max heap instead of a min heap. And the great thing about doing this change is all it requires you to do is take all those less thans and turn them into greater thans, and all the less than or equals, turn them into greater than or equals. The pseudocode doesn't change any other way. That's literally it. Why? Because that's the only times we make key comparisons is we use inequalities like these. Obviously, in your programming language, you might use like a compare or compare to kind of function. But either way, this is generally the behavior you need to change, to turn one from the other. That's why I haven't addressed max heaps really, is that there's an easy way to transform one to the other by just simply tweaking around with the inequalities when I do the key comparisons. So here's the process. I'm going to start off with heapify. I'm going to build out of array a heap. So I'm not going to add any more memory. I'm just going to use array A as I get it. I'm just going to turn that into a heap. I can use heapify. That takes linear time. And then what I'm going to do is I'm going to start at the end of my array. And what I'm going to do is I'm going to swap this with A sub 0. So the first position. And then what I'm going to do is I'm going to update the heap appropriately using bubble down. Now, the way I'm going to use bubble down is a little different than I've done it up to this point. Notice that I don't have n minus 1 here, I have I minus 1. What's going to happen is a part of this heap I'm going to use to contain the sorted elements that I have. So I'm going to make sure that I minus 1 is there to kind of be as a safeguard to make sure I don't touch any of the sorted part of the array. Why? Because the heap is only going to consist of some part of the array. So what you might ask, what the heck I just described to you? Well, now I got rid of the extra space. Everything's done within one array. And I've described to you heap sort. This is heap sort. And so now notice I use a constant amount of extra space. This is an example of what we call an in-place sorting algorithm. So all you do is, so when I talk about in-place, I'm meaning that you use a constant small amount of memory. So constant amount of space that gets used in addition to the input. So sorting algorithms, this is something that some people bring up, is the so-called in-place algorithm versus one that isn't. What it simply means is that if I give you the input of the array, I want to know, so you'll take the input array in, I want to know, is there a way you could transform the array without using extra memory other than a constant amount? So I give you an input array, your job is to transform it into a sorted array, but you're only allowed to use a constant amount of memory. That's what I mean by in-place algorithm. So that's how heap sort works. So just because of the time we currently have, when I come back, I'll do an example with you for heap sort, and then we'll be doing our last application. I wanted to show you both, but we'll see it next time, okay? So that being said, I want to say thank you very much, and have yourself a beautiful day. I'll see you later.